Hi, welcome back. So here we are. We've got an interesting problem to look at. So it's labeled as combined loads, but in the reality, it's a fairly straightforward bent beam, if you will, with a uniformly distributed load on the bent component. So where this becomes a combined loading problem is that when we look at the cross section where our point of interest is, we're going to end up with not just a bending moment in a shear force, but we're also going to have a normal component because of the way the structure is loaded. And so that means it's going to be axial load, if you will, in addition to the bending. And we already know from the last problem that that's going to change our stress distribution. So we're going to have a look at it and do it out from first principles and have a little bit of fun with it. The geometry in this case is a little bit interesting. So just from a perspective of growing our appreciation and understanding of how to approach these problems and to problem solve their geometry, it's going to be interesting too. So you see where point C is. It's on a cross section 1.5 meters from the left hand support A. So it's 1.5 meters off to the right. And when we look at our cross section up here on the left, it is at the top left corner of that cross section. And so now we're starting to see where your appreciation for the stress is and how they vary across the cross section depending on the nature of the loading that you're looking at really is going to start to matter, as well as orientation and everything else. Like I say, this is just one in a series. We're going to get more and more complex. And so we're going to start almost to take for granted some of the lessons that you've learned in the previous problems and expect you to be able to envision and picture the stress distributions that they are independently causing so that we can combine them in a logical way. So anyway, that's enough chat. Let's get on with solving this problem. Of course, the first step is to set up a free body diagram. I've already laid out the center line of our free body diagram, and I'm going to go on about labeling it. So let's get our reactions in here. So we have a pin support at A, so we're going to have a reaction RAY and RAX. So we'll get those in here. And at our roller support at B, and we see that it is on an angle, so it is perpendicular to the cross section or parallel to the cross section at that point. So we have to draw it in that direction, and that is going to be our. Let me draw this down here so we stay out of the way. Our RB. Now, when we look at our geometry, it is worth noting just that we do know the line of action for this force. And so that's going to be a 3, 4, 5 triangle to line it up perpendicular to the beam at that point. And we can see that. So I still have to add our uniformly distributed load. So let's put that in here. My ruler and connect those together. Now, I think just because things are going to get a little bit complicated in this case, I am going to put in my equivalent point load at the midspan there, indicated as an equivalent point load. Again, as with the reaction at B, we know the geometry of this in that it needs to fit that 3, 4, 5 triangle orientation. So that it's lining up appropriately for the force being applied. Now, that's our free body diagram, but what we really need to get out of this is some of our geometry, if you will. And really by that, well, I guess what I'm talking about are the right perpendicular distances so that we can solve for our reactions. So I'm just going to label something in here. So if I draw this line in here, and I label that angle as theta, then if I were to draw this line in here, then this also would be theta, which is useful. And I'm going to draw in or extend. So I need to extend these lines down and try to keep them so that they look like what I'm doing. Because if I'm doing moments about A, eventually I need to get my perpendicular distance to those. And so I need to have a line that hits all of them at right angles. And because of where theta is, I'm going to label one more. So we also know that this angle in here is equal to theta. So if I look at the triangle of the bent section, we see it is a 3, 4, 5 triangle ratio. So 3 up, 4 horizontal, and 5 on the hypotenuse. And that, it's a right-handed triangle for theta. So if I go over to my large triangle that touches on A, that also has to be a 3, 4, 5 triangle comparison. And when we look at it, we can see that this side is 3, this side is 4, and the hypotenuse is along that axis there as 5. And we can start to get some dimensions from that. So the first 2 dimensions that we can draw directly, so that the length of the bent section is 2.5 meters, so 1.25 meters for each of them. So I'm just going to write those in here, 1.25 meters and 1.25 meters. But we're going to have to calculate the other dimension going from point A to that first line. And so when I look at that, we know that that is going to be equal to 4/5 of the horizontal distance of 4 meters, and that equals 3.2 meters. So in a little bit of time looking at the geometry of the structure, we're able to get the essential dimensions that we're going to need in order to be able to solve this. The other thing that I'm going to do, just because I'm going to work that way, is ultimately I'm going to break this one down into its x and its y components, and I'll label those as RB, Y, and RBX. And of course, once we solve any one of those, RBY, RBX, or RB, because the orientation is known, we know all of them. And so keep that in mind. And with that, I think we're ready to move on to our statics. So let's get up here to the top and say statics, or solve for reactions, if you will. And I'm going to jump in. I'm going to start with my sum of the moments about point A. I'll use clockwise positive as I typically do, set it equal to 0. And let me see, the one thing that I didn't do, I said I was going to put in my equivalent point load, but I never actually calculated it. So let's do that here. So our intensity is 50 kilonewtons per meter, and it's applied over 2.5 meters. And so that is equal to 125 kilonewtons. And so that's going to be useful to us. So back to our statics, sum of the moments about A is equal to 0. And so moving clockwise positive, the load, or the externally applied load, that UDL, we can just use its equivalent point load. So that's 125 kilonewtons. And its perpendicular distance is the sum of the 3.2 meters and the 1.25 meters. So we'll put that in here, 3.2 meters plus 1.25 meters. And then going counterclockwise is our reaction at B. And our reaction at B multiplied by its perpendicular distance would be the sum of the 3.2 plus the 2.5, or the 2 times 1.25. So 3.2 meters plus 2.5 meters. And run those through our calculator, we can get RB is equal to 97.59 kilonewtons. So in anticipation of doing my next two statics equations, some of the forces in the x and some of the forces in the y, I'm going to very quickly go ahead and calculate what my RBx and RBy are. And I can do that just by multiplying the 97.59 by either 4/5 or 3/5, depending on which end of the triangle they are. And so RBy is equal to 4/5 of 97.59, which is equal to 78.07 kilonewtons, and RBx then is equal to the 3/5 of 97.59, and that's equal to 58.55 kilonewtons. And that'll just save us a little bit of writing as we do this. So we'll start with sum of the forces in the y direction, set it equal to 0. And we're going to see we have RAY unknown pushing up. We have the y component of our UDL, so it's on that same orientation. So that's equal to 4/5 of our 125 kilonewtons, and our 4/5 of our RB, or we've already calculated it out to be 78.07. So plus 78.07 kilonewtons, and that allows us to calculate RAY to be equal to 21.93 kilonewtons. And very quickly, some of the forces in the x direction equal to 0, and we can start with RAX, again unknown, going to the right, and now we're going to subtract the x component, or 3/5 of the 125 kilonewtons, which is our UDL, and add 3/5 or RBx, 3/5 of 97.59, which we already calculated to be 58.55 kilonewtons, and that allows us to get RAX equal to 16.45 kilonewtons. And I'm just going to transfer those over here. So RAX 16.45 kilonewtons, RAY 21.93 kilonewtons. And we're almost away to the races. So now that we've got the structure as a whole solved, what we need to do is we need to use our method of sections and derive the internal forces occurring on the cross section at C, or 1.5 meters from the support at A. So let's get that. We'll say determine internal forces and this is the cross section at C, not at C itself. C is a point, but we need to do the cross section first. And to do that, we're going to do a quick partial free body diagram. So I'll just get my section in here. So we're going to be going from support A to the cross section at C. So that means I have my reactions RAX and RAY on the left-hand side, and they have 16.45 kilonewtons and 21.93 kilonewtons. And then I have my internal forces at point C. So we have our shear force, V at C. We have potentially a normal force, N at C, and a bending moment, M at C. And I've drawn them all in as if they were positive in accordance with the sign convention that we've been using up until now. And finally, the last thing I want to do, just because I don't have any dimensions on this, is I should label those in here at 1.5 meters. So it's absolutely obvious. And then we're back into statics and trying to solve that. So now we're isolated on this partial free body diagram. I can do sum of the forces in the y direction is equal to 0. And we see that's 21.93 kilonewtons minus V sub C, or V sub C is equal to 21.93 kilonewtons. And we can do sum of the forces in the x direction equals 0. So that's 16.45 kilonewtons plus N sub C. So our normal force is equal to minus 16.45 kilonewtons. And finally, we can do some of the moments. And we'll all do some of the moments about A equal to 0, clockwise as positive. And so that's equal to our V sub C multiplied by 1.5 meters. V sub C, we already know, is 21.93 kilonewtons, so we can substitute that in there. And from that, we have negative mc because it's trying to go counterclockwise. And our moment then at C is equal to 32.89 kilonewton meters. And so we have all of our internal forces at C. So now the last step we have to do is actually look at each of those and say, okay, what stresses are they causing, and make sure that we incorporate those into our problem. So typically the way I do this is I first look at the contributions to normal stress, and then I'll look at any shear stresses that are coming out. So I'm going to say determine normal stress at C due to N, because it's effectively an axial load, so that's going to be causing a normal stress. And the formula appropriate to a normal stress is our stress at C is equal to our N sub C over A. So that's P over A, but I've substituted in the actual nomenclature that we've been using in this case, which is N. And we set that equal to, we have minus, this is in kilonewtons, I want to work in newtons, so 16,450 newtons divided by the area, which we don't know, is 50 millimeters times a height of 250 millimeters. And that gets a value of negative 1.316 megapascals. And because it's negative, we know that that's in compression. Now, to keep this all oriented, what useful to me sometimes, I like to draw my little differential element, if you will. So if that is here, And just I won't draw it in on everyone, but just so we get the orientation. So this is my X direction here. And so the stress is a normal stress going in the X direction. And so it's in compression. So I can draw in my normal stress. In this case, going like that, and a value of 1.316 megapascals. So that's it. That's the normal stress due to N. We just carry on. We say, okay, determine. We have one more force causing a normal stress. So we'll say normal stress at C due to our moment. And so normal stress at C due to a bending moment. So that would be our negative my over I. And so we have negative 32.89 times 10 to the 6 to get that into newtons and millimeters. Our y is half the height, or 250 millimeters divided by 2. Times 50 millimeters times the height, which is 250 millimeters, which is cubed, divided by 12. So that's the formula for I for a rectangle, bh cubed over 12. And it's bending about the, which is it? It's the z-axis, I guess, in this case. And so we are able to look at that, and we get negative 63.16 megapascals, which also is in compression. And again, I'm just going to draw my differential element, help keep it all straight here. Same orientation. We know it's acting in the X direction. We know it's in compression, so it's going to look very similar to what we did in the last one. And a value of 63.16 megapascals. So the last thing we need to consider is determine shear stress at C due to V. Of course, that's transverse shear due to bending. And you will recall that that's related to Q. And in this case, we are at the extreme fiber on the top of the beam. We know that Q varies from a maximum at the neutral axis to 0 at the extremes. And it is the shear stress due to it is proportional to Q. So where Q is equal to 0 at C, therefore we can say tau is equal to 0. If we were at some other point on the cross-section, we would have to calculate Q for that point on the cross-section and determine what tau would be as a result of that using our VQ over IT. So I'm going to draw that out. I'm going to put in my differential element as we did before. And despite the fact that we know it's going to be equal to 0, we know that Q is acting on this face vertical. And so I just want to show that so that we're keeping in mind what face we're working on, because we're getting ever more complex in these combined loads. And that's tau is equal to 0. So with that, the last thing we have to do is we have to combine them. I'm just going to use this little open space here. Combine like stresses. So you combine your normal stresses on the same face, you combine your shear stresses in the same face, same direction, like stresses at C. In this case, the only ones with a non-zero value are normal stresses, and they are both in the X direction. So we have our normal stress at C is equal to our normal stress due to N plus our normal stress due to bending, and that's equal to negative 1.32 megapascals minus 63.16 megapascals, and that's equal to negative 64.5 megapascals, and that's compression. And so for one last time, we're going to draw our differential element. We'll just draw it in there, and we'll put our normal stresses. We'll show them as compressive on that X face and give it a value of 64.5 megapascals. And so there we have really our first extensive application of combined loads. So we have stresses resulting from the bending moment. We have stresses resulting from a normal stress because of the orientation of the loads. Potentially we would have had a shear stress, except we were at that extreme fiber, so we considered it, but we determined that it was going to be equal to zero. And then we went through the process of combining like stresses on similar faces or on the same face. And so that's a whole series of concepts which we're going to see carried through time and time again as we look at ever more complicated problems coming up. So again, hopefully that was useful to you. I will put a link to the next video in the series, and I hope you follow along and are able to grow your appreciation and skill in this essential area.